So hello everyone, welcome to our channel. So today we will discuss the topic anisotropy of elastic behavior. That means we understand that whenever the material behaves elastically, then it is understood that if you apply the force in different directions, then the elastic behavior will be different. That means elastic constant is basically different in different directions in the basically crystal. So this is a diagram to make you understand first the Hooke's law, then we will understand how it varies from different direction. So see, this is the bond energy curve, and in x-axis it is the distance between the two atoms, and in the y-axis it is the potential energy. So when the two atoms are at infinitely long distance, right, and they are separated by very long distance, so the energy between them is zero, right? When the two atoms are brought together, then the energy curve follows like this, and this becomes negative at the location where there is a equilibrium between them. So what kind of equilibrium is there? uh, the equilibrium exists between the repulsive force and the attractive force. So since there are two atoms, right, so these two have the masses, so there will be some attractive force, okay, and there will be the repulsive force also, because both will be of the core of this will be positively charged, right? So there will be certain amount of repulsion, okay. So when it maintains the equilibrium, so at that position the energy is the minimum, then again the energy basically increases, okay. So we can see the force diagram also. This is the force diagram of the same thing. So we can see that the point where it is the minimum, the force is zero, right? That means the force is balanced, the attractive force and the repulsive force will be balanced, right? Okay, now this energy curve which is there, so this energy curve is basically defined in terms of the displacement, okay, because we can see that as the distance it is there, right, suppose this is the equilibrium distance, that is a naught, right, and if you increase the distance between them, like suppose you increase it by some value a, right, so the difference, suppose then it will be a minus a naught, so it has some good difference, and at this distance basically the potential energy it has changed. So that means we can say that this potential energy we represent as phi, okay, so is a function of distance, right, and this is basically described as a this term is described in the form of Taylor series, okay. So this phi which is dependent of u will be this phi naught plus d phi by du, okay, times u plus d2 phi by d2u du square, this will be half, then u square plus dot, something like this. So I have taken the reference from the data book, so from there you can also see. So basically this is the equation of the energy curve which is there, right, and if you see the energy curve, then this is the bottom point, right. So at this bottom point, so the energy will be the minimum, right, and when the energy is minimum, basically the force is basically zero, right. So this force we know is a function, or that is a differentiation of this energy with respect to the displacement. So force is nothing but the differentiation of this energy by displacement, right? And at this point basically this will be equal to 0, right? Okay, and one more thing, this u, basically u is called the displacement. So u starts from this position. At this position the u is 0, and here it will be in positive, and here it will be in negative, right? So this is nothing but u is equal to a minus a naught in the positive. Okay, so now guys, now we have the equation that is phi u is equal to this, right? And we need to see at this point the minimum point. So this phi u we can write as phi naught plus this term, that is d phi by du, can be 0, right? Because this is nothing but the differentiation of energy with respect to distance, right? So that is given by force, that gives the force, and this force is equal to 0 at minimum energy point, right? Here the force is 0, F equal to 0, right? Then plus half d2 phi by du square u square, right? So phi u we can write half d2 square by du square u square. Okay, okay. Now guys, for the elasticity calculation, we will write that the force which will be calculated, so that should be the differentiation of this phi u by du, right? So in the generalized form, so this p we can write d phi u, that is phi naught plus half d2 phi by du square, then u square divided by du. So since this is phi naught is a constant term, so it will be 0 plus half d2 phi by du square, it will equal to 0, then this will be 2u, right? So we can write p is equal to d2 phi by du square at u equal to 0, then times u, right? And this term will be a constant term, right? Because this is the double differentiation of this at location u is equal to 0. That means this will be a fixed term. So that's why we can write p is equal to some constant k into u. So p is nothing but the force. So force equal to some constant k into this displacement, and this is the form of this Hooke's law, right? Okay, and if you understand the geometry, then this term, that is double differentiation of this, is nothing but it is called as the curvature. Okay, that means if the curvature of a graph will be more, then this value will be more, right? Then we can say that the elastic constant of that material will also be more. So we can understand from here that suppose you have two curves, one is like this, okay, sorry, one is like this, and second one I will draw over there only. Second one, it can be like this. Third one, it can be like this, right? So your 1, 2 and 3, right? So this is your 1, then this is your 2, then this is your 3. So E of 1 will be greater than E of 2 will be greater than E of 3. Okay, because here the curvature of 1 is higher. Okay, and there is a steep change in graph 1. Okay, and guys, now from here you have understood that this is Hooke's law, and this d2 phi by du square is nothing but the elastic constant, right? And this term, that is the phi u, is a function of distance between the atoms, right? So the distance between the atoms will be different in different direction. If you see the crystal structure, suppose you have the BCC, right? I am drawing it to understand. So if we have the BCC, now suppose this is the direction, so this will be a direction like of type 100, right? So here the distance, this distance will be different than compared to this direction. So this is of type 110, right? Here the distance will be like a, but here the distance is root 2a, and the next one, like this is of type 111. So here the distance will be of this nature. So the u term, that is the energy term, here it will be different, right? So u term for 111 will not be equal to u term of 110, u term of 100. That means the energy curve will be different, and since the energy curve will be different, that means the E value will be different. Okay, so from there the anisotropy exists. Okay, if it is a pure single crystal. Okay, so that's why, see, when we have a very big material and we have many grains, right? When we have many grains, then what happens, each grain will show some anisotropy, but effectively, suppose this is the anisotropy from other grain, but effectively if you combine all the grains, then the properties gets average out, right? That's why we get a common property when we have multi-grain material, right? Okay, so hopefully this will this you might have get clear about this, so it may help you in your examination or your understanding. Okay, so thank you all.